our next talk will be Kubernetes security, talent and opportunity from Marc. Enjoy it.
Thank you. So hello everyone, my name is Marc. I've been working for IT security consulting for the last 10 years, maybe in the areas of technical security, pen testing, application security, which has eventually led me to Kubernetes security topics. I'm working for Certitude. We're a consulting company based in Vienna, advising clients on IT security matters. And we are hiring, so if you're interested, get in touch. So what am I talking about today? Maybe let me ask you a question first. Who of you has already worked with Docker containers? Okay, most of you. Who of you has already run their containers in a Kubernetes cluster? Okay, that's good, most of you. So who of you has already worked with or thought about Kubernetes security topics? A few. Okay, that's perfect audience. So I will give you a brief introduction. I will keep it very brief into containers and Kubernetes. And then we will talk about security topics like container isolation, Kubernetes attack vectors, common vulnerabilities that we see in the wild. There's this particular issue with multi-tenancy. So how can different customers work on the same cluster? Is it even possible? And we will also talk about opportunities for security. So there are some new risks, but there are also new challenges that we should also be aware of. So this is a basic overview of a Kubernetes cluster. On the left side, we see a Kubernetes master node, and on the right side, a worker node. Usually a cluster has 3 to 5 master nodes, at least one, which is kind of the control setup of the cluster. And on the other hand, on the worker nodes, we have maybe 3, maybe 100, so it could be a few hundreds. This is where the actual workloads will be deployed. So Kubernetes is an orchestrator for Docker containers. We have microservices, so we don't have large applications anymore, but we kind of have a lot of different components, APIs or whatever, but they need to be orchestrated because we need many of them and we need to kind of organize that and make sure that network setups between them and redundancy and all these issues are configured and addressed. So Kubernetes is what makes this, or what allows us to orchestrate these containers, and there is the Kube API server on the master node, which is the most central component of Kubernetes, and it's an API, and everything that we do in a Kubernetes cluster goes through the API. The etcd is a database that stores our state. The controller manager makes sure that, or the managers make sure that the cluster is in a good health, so whenever it detects something that's not as it should be, then it tries to restore a good and healthy status in the cluster. And the scheduler, as the name says, is for scheduling workloads. So whenever we want to run a new container in a cluster, then the scheduler decides which node this workload will run on based on the configuration. When we are talking about security, it's also very important to consider how nodes work. So we have a kubelet. A kubelet is like a Kubernetes agent. So whenever we want to have a node that should be part of a Kubernetes cluster, we install the kubelet and configure it so that it kind of can connect to the API server, and that makes our nodes part of the cluster. And the kube proxy component is also a kind of an agent running on each node, but it's for networking. So it configures the networking on the node so that the traffic reaches our containers. When we zoom into the kubelet, so into this agent on our nodes, then we have the following components. On the left side, you have the kubelet, and then we have a container runtime that could be Docker, as it was until now, let's say, most of the time. But in future, will probably be more something like CRI-O or containerd. But yeah, in simple terms, it's kind of a Docker runtime. And yeah, more technically, we have the runC component, and the runC component is, it actually configures our containers, which are processes, and it makes sure that they are running on the operating system, kind of isolated with their own file system, things like that. And these green bubbles, CRI and OCI, are standards. So it's the open container interface and the container runtime interface. And it makes sure that all these components are pluggable. So Kubernetes is very modular, so you can exchange certain components. I don't know, do you see my mouse? No, okay. So formally, or you could also use Docker instead of CRI-O or containerd, and you can pick a cryo or you can pick containerd, so these are options. And all these standards make this possible, make it so modular and so flexible. But it's also difficult to talk about Kubernetes security because I'm talking about plain Kubernetes, the default setup, so to say. But there could be many flavors, like with Linux distributions, there are many of them. There are Kubernetes objects. So Kubernetes objects are configurations that configure our workloads. When we have Docker containers are not really known by Kubernetes. Kubernetes only, they are known, but they are not objects. Actually, the smallest object that's used in Kubernetes is a pod. And within a pod, you can configure your Docker containers to run. There are other objects like a service. A service makes sure that your traffic reaches your pod. So it's a configuration that just says, whenever there's traffic to this IP and this port, it should be destined for one of these pods. Then there is, for example, a replica set, which makes sure that there is some redundancy. So I can configure a replica set where I say, okay, this pod should run 3 times, and there is another pod that should scale 10 times for redundancy and for scalability. And there are many objects. You don't have to understand all of them. The basic one or the main one is a pod, which basically means your container or your containers. And all around that is used for networking and for scalability and things like that. So many of you probably have seen a Kubernetes pod configuration like that. So on the left, we configure a pod. Its name says it's an Nginx pod, because it's running an Nginx image, so like for a web server or reverse proxy, and it has a certain port. If we run that configuration on the left, then our Nginx will be running on Kubernetes. So Kubernetes will pull the image, will start the container, and the pod will be running. On the right side, you see a service. A service, as I said, makes sure that this Nginx is reachable on the network. And the cool thing about services is I could run 10 pods, and I only have one service IP and URL, and it will be used for load balancing. So I have a kind of a load balancing integrated into Kubernetes. For security, quite important is the idea of namespaces. You know that from other technologies. When you have certain configurations, you can define a namespace, and a namespace is it groups your objects, and you can, for example, define role-based access control, so authorization based on your namespaces. You could have, for example, a block service or your block application running in one namespace with its own developers, and you can have a web shop that's being developed by other developers, and they have their own namespace, so they shouldn't interfere too much with each other, and you can use certain access control mechanisms to group these objects and to make sure that every developer can only access what it's supposed to access. There's also admin users, administrative users that have the kube system namespace. It's the default system namespace for all the system components itself. So there are certain containers that are running in each cluster to make sure that within the cluster we have DNS, we have networking, we have maybe a dashboard or something like that. So whenever a request reaches our cluster, it will be authenticated. So the cluster, the API will check who are you. It will be authorized, so the cluster will check, is this user allowed to create, read, update, or delete this object? And then there is admission control, which even looks into your requests and looks into the details and determines if you're allowed to do that or not. And the admission controller can maybe deny it or can even rewrite your requests. We will see why admission control is quite important in a later example of an attack. Networking, so in simple terms, there is an overlay network. So we have our physical network, that connects our nodes, and then we have an overlay, a virtual network that's handled or managed by the cluster to make sure that every pod has its own network namespace, its own ETH0 interface, and that the pods can connect to each other on the pods can reach each other on the network, no matter if they are on the same node or if they are on different nodes. What's important about networking in Kubernetes is it's done by plugins. So it depends on which CNI plugin you use. You get different kind of networks. So the CNI plugin basically configures your IP addresses for your containers, And for example, maybe your firewall rules, some of them support firewall rules, some don't. So actually that's really done by a plugin. Without the plugin, networking would not really work. I won't go into too much detail, but we know this graphic from before, and as well as there is a run C to start the container processes. There's the CNI plugin, for example, Calico is one of them, to configure our virtual interfaces and give them IP addresses and make sure that they can reach each other. Okay, so that was a brief introduction, so I hope, I saw that most of you have already some experience with Docker and Kubernetes, so I hope that was enough to give you a basic understanding for the next few slides. Let's look at security aspects. So container isolation, of course, is vital for a secure cluster. When we compare virtual machines with containers, many of you probably have seen a graphic like that. On the left side, you see a classical virtual machine example where you have a host kernel, a hypervisor, then you have guest kernels, and then you have the containers or applications. And in the container setup on the right, you only have the host kernel, then you have a container runtime, and then you have the applications. And actually, the containers run directly on the host kernel. There is no hypervisor or no guest kernel in between. Yeah. To make sure that the idea is these containers should not see each other. They should be like a virtual machine. Every application should be isolated. It should be, the idea is also to keep it secure, but also it should not interfere with other containers. And technically, a container is just a process. In the Linux kernel, there is no container by definition. There is just a process with C groups and with namespaces. And C groups and namespaces are kernel configurations that make sure that these processes are better isolated than the normal processes. And so all the isolation security really depends on what runtime you use, because the runtime configures the run C, eventually configures the namespaces and the C group, so it tells the Linux kernel how to create these processes. And it also depends, of course, on your Kubernetes configuration, because Kubernetes will be the high-level configuration, which results later on in the container configuration. So namespaces are a Linux kernel feature that is very important to understand containers. We have a mount namespace, we have a network namespace, and for example, a network namespace makes sure that every container or every pod actually gets its own network namespace. So it has its own virtual network stack. And for example, that means that every process can use the same port or can listen to the same port. So in a normal system, if two applications want to use port 80 for a web server, you will have a conflict. It will not be possible. But within containers, that's possible because they have their own virtual network stack. And virtually, to them, it seems that they can both use the port 80. But then, of course, on the node, it's mapped to another outer port. But yeah, for the container thinks it's the only thing running on the machine, and it has its own network, and there is nothing else, and there is no other process. So this is what the PID namespace does. It makes sure that a container cannot see other processes. UTS namespace makes sure that the container can only see its virtual host name, which is different from the physical host name. The IPC namespace makes sure that virtual memory is isolated between containers, so that one container cannot, like one process cannot interfere with another process over virtual memory. So namespace is really isolating processes within the Linux kernel. There is a special namespace, which is the user namespace, which virtualizes users. So when you root in a container, you wouldn't be root on the host. That's something you could do with that. But it's usually not enabled by default because it has there are some problems with volumes or with storage. So it would be good to enable it. It would be really good for security. We will see later on why. But by default, it's usually disabled. And then there are capabilities and mandatory access control that also put some restrictions on these processes. Capabilities, normal Linux capabilities, so they are restricted or reduced to the necessary minimum. And seccomp and, for example, SE Linux or AppArmor also restrict system calls, and they restrict file access and things like that. So as we can see, there are a lot of normal Linux kernel features involved that eventually lead to containers. So containers is not a kernel feature by itself. It's just all these kernel tools that are kind of combined together to make what we know as containers. Yeah, seccomp profile, it's not a talk about seccomp, but yeah, it filters system calls. That's important because there are some dangerous system calls like, I don't know, a reboot or an unshare, which could even be used to bypass capabilities and other things. Yeah, so it's quite an important feature, and yeah, what's important to know is that by default in Kubernetes, seccomp is not enabled, so there is no filtering of system calls with by seccomp. But you can enable that. Yeah, you can enable it manually in the cluster, either for each pod, or you can even change the default. But that's something you have to do yourself. Otherwise, you won't have a cluster that is secured by seccomp. And actually, without seccomp, we can even bypass the capabilities because we can use the unshare system call. Yeah, because no system calls are restricted, so we could use the unshare system call to bypass the restrictions by capabilities, so that we get the sysadmin capability. So yeah, that's something you should know if you have a cluster that you want to keep secure, that you want to harden, then make sure that seccomp is enabled. This is an example of a seccomp configuration that logs certain system calls. Actually here there is a list of system calls that are allowed. Everything else will be logged, and eventually you can even, of course, deny it, and then yeah, only your allowed system calls will be allowed. There is a default seccomp profile that Docker users or some runtimes use that you can have a look at, and it's quite okay by default. You can even restrict it further by manually removing allowed system calls. And also, yeah, SE/Linux or AppArmor, depending on your node OS, it might be enabled by default or not. So it's different on a Red Hat CoreOS than it is on another distribution. And yeah, what it does, it restricts access to certain file systems like the proc directory or the sys directory. It denies mounts and things like that. So it's also quite an important mechanism to keep your processes isolated. Let's talk about users and user namespaces, because yeah, it's quite important it would be quite an important feature to security, but it's not enabled by default, and here is maybe why it would be a good hardening measure. We see a container here in this graphic which runs an image, and this container could be run as root, which means sometimes that's necessary because there are some legacy applications that need root privileges to be working properly, or sometimes it's just a misconfiguration. And yeah, normally if everything goes well, the user should not be able to escape its container context. But if something goes wrong, that might be possible. And if it's possible, then you automatically root on the host. If you enable user namespaces, then there is the UIDs are virtualized, so to say, and the roots, the UID 0 in the container gets mapped to UID 11111, for example, which means a non-privileged user. And that means whenever there's a container escape, when something goes wrong, then the user is restricted at least to a non-privileged user. So yeah, I hope that we will see user namespaces become a default in some future version sometime. When we look at the big picture and what would be the attack vector of a cluster, so what would we need to do to actually really get cluster root access? Yeah, it's not easy because there are so many layers, like in an onion. Yeah, you have your application. So if you're really outside the cluster, we are talking about a web application, for example, you would really need to find a vulnerability in the application that leads to code execution. Yeah, once you have that, you will be within the container. If the image is not hardened, you might find a shell there and other commands and tools that are useful to eventually maybe escape the container with a kernel vulnerability, a runtime vulnerability, whatever. We'll see a few examples of that in the next few slides. And then from there, when you can really escape the container, you have compromised the nodes, and from there you can maybe find some, in the kubelet configuration, you will find some access credentials to the cluster, and you might be able to get access to the cluster and to the API server and things like that. Yeah? So it's definitely not easy, but there are a few security boundaries you have to jump through, but it's not impossible. When you are in a shared cluster, when maybe one of your developers doesn't really protect his or her kube control. The kube control is the client to interact with the cluster. And when you're a developer with cluster access, then you might have some credentials for the cluster on your laptop. And for example, if these get leaked, or if otherwise there is a multi-tenant cluster with multiple different teams and multiple different clients, then of course you're directly like on the cluster, so you can jump through the first few difficulties, and yeah, the only thing you need to do is to find some sort of runtime or kernel vulnerability or configuration issue to access other namespaces and other users, other clients. There is a useful attack matrix released by Microsoft which summarizes a lot of Kubernetes attacks, so it's quite a useful resource, at least at the time. At least this version that I looked at, it was not really complete, so I missed runtime and kernel vulnerabilities there, but still it's quite a good overview. Yeah? And also this resource is quite useful to see what kind of configuration issues could lead to which attack vector. So privilege flag, for example, is a configuration for a pod. You could configure the privilege flag for the pod, and that means that your containers will not really be isolated at all, so they will kind of be run with executed privileges. Sometimes that's necessary for some cluster-specific tools, but it's also dangerous, so you should be really careful about that. Or sometimes it's enabled for debugging, and then they forget to disable it. Eventually, like if you have a privileged pod, then this pod is able to compromise the whole cluster and even access other workloads and things like that. And so other configurations like host PID, host path, they disable some namespaces, so they disable some security protections around your processes, so they lead to attack vectors as well. Yeah, what are common vulnerabilities that we see in the wild, that we see during pen tests that we can exploit? So outdated software, obviously that's a common one, and Kubernetes has like a lot of software involved. So there's the runtime, there is the cluster, there is an etcd, so there is the application itself, there are images and base images. So there are a lot of things to keep patched and keep updated, which is not always easy for many organizations. And yeah, outdated software, of course, as we know, lead to certain vulnerabilities. Also, like recently or every month we find some new CVEs, and some of them severe. Outdated runtime. As we know, the runtime sets up our processes and our namespaces and our C groups, so it sets up the container isolation. So if the runtime is outdated, there might be some bypasses and some exploits. So there's an example, the CVE from 2019, but it's a cool example where basically, or in simple words, you have an image where you change the entry point to proc self access. So let me start it differently. So whenever you start a new container, the runc init. So the container is created, the namespace, the process, and within the process, the runc init is being run. So this is kind of the init process, and from there, this init process will then start your user process, and then your container is kind of set up. And there was a vulnerability which allowed that you could override the runc init within the container via the proc self exe symbolic link. And the symbolic link actually linked to the host's user sbin runc. So from within the process, you could override the host's runc, which is the container runtime process. And yeah, as we know, when we can override an executable on the host, of course, we can break out from the container. Yeah, this is one example of a runtime vulnerability, and this could be prevented actually when you're not running the container as root. So this is only a vulnerability that only applies when the container is not configured with non-root user. Yeah, of course, user namespaces would help here as well, because once this exploit occurs, then at least on the node, this container would be restricted to a normal user. Yeah, outdated kernel. Of course, our kernel, we share the same kernel. In contrast to VMs, where we have a different guest kernel, on containers we are all on the same kernel. So yeah, of course, a kernel vulnerability, a kernel exploit could lead to a container escape. And yeah, actually I can show you a demo. This is just to get an idea of how kernel exploits are dangerous, or how, after a kernel exploit, it can be quite easy to bypass the whole kind of Kubernetes security ecosystem. It's an old vulnerability. It's in this demonstration I used Dirty Cow. Yeah, I know it's old, but there are some recent ones as well, which would lead to the same issue. So I think its text size is large enough. What I can show you is there is a Docker file, which is basically a normal Ubuntu image with the latest updates and with some tools I will use from an exploit. If they are not in the image, or in the image built in, then of course you might also be able to download them at runtime, because in many setups pods have internet access. And so to now build this container, where is my cursor? Sorry for that, there is a screen resolution issue. Let me fix that first. Yeah, maybe let me just scroll. Yeah, okay, sorry. So we built this Docker image. Okay, that doesn't work. I have to change the resolution, sorry. Yeah, so we can now build this image. We'll just call it escape demo. So it's now built. And let me show you. So I'm running as a normal user on my host system here. Now I run the container. So now I'm the user John in the container, so normally I should be quite isolated. Let me now, so this is actually the exploit code. Oh. I will compile it. Look at the IP address. So now I will call the exploit with my local IP address, and as you can see, I'm now again root on the host. So I have escaped from the container and even escalated to root. So this will be how easy it could be to escape a container with a Linux kernel vulnerability. How did that work? Just to give you an idea, Dirty Cow, it's a few years old already. It's a race condition in virtual memory mappings that should usually be read-only, but if you have a copy on write, there was an issue that you could even overwrite the original, which normally should not be possible. And then there is, in Linux, you have different processes, and you have the VDSO shared memory, which is used as an optimization to optimize some system calls. For example, that when your process wants to get the clock, which happens very often, then normally there would need to be a context switch to kernel mode, which would cost a lot of time and performance. So what they did is in Linux they have a shared memory mapping called VDSO, and the time is always kind of pushed into these mappings. So the processors, when they want to read the time, they don't need to have a context switch, and they can just read it from their process. So the issue with shared memory mappings with dirty cow is that you could overwrite shared memories that normally should only be read-only. So our container on the right has this VDSO mapping, and this vulnerability would allow it to write to the VDSO, which would of course then have an impact on all the other processes. And the process on the left, the process A, is a root process. So whenever this root process next time calls the clock get time function, then yeah, we have overwritten it, so we can execute our own code. And this will be, or as an example, it was a reverse shell. So this is how we escaped from the container and even got root on the node. And there are many kernel vulnerabilities being published every the critical ones every couple of weeks or months, and some of them, of course, might be as severe as this one. Another kind of vulnerability that we often see is role-based access control issues. So it's quite tricky in Kubernetes to have a good access control configured. So you notice this graphic from before. We have authentication to identify the user. We have authorization. But our authorization is quite limited to create, read, update, delete. So I can allow someone to create an object. I can allow someone to read an object, to update it, or to delete it. But I cannot configure details. So when someone wants to create an object, I cannot say which object or which details of which configuration of this object is allowed and which not. And this means that if you give someone create pod privileges, this user will most often be able to access other namespaces in the worst case. So in this example, this user should not be allowed access to pod A, because pod A belongs to another namespace, another team. The user shouldn't have access to it. So when he calls the API and wants to read something about pod A or make a kubectl exec, access will be denied. But if the user has create pod privileges, because the user needs to create pods in its own namespace, then the user could create a privileged pod, which is just a pod with a special configuration inside it. And from this privileged pod, of course, which is running on the same nodes, then the user has root on the node and could access other workloads. So it's quite important to understand that the role-based access control in Kubernetes only applies to the API server and to the objects, but via creating processes and creating privileged processes, you can kind of bypass this with the create pod privilege. So how can we restrict that? We can restrict that with admission controllers. So admission controllers, once it's authorized, so once the user is authorized to create a pod, the admission controller will check the configuration, will see, oh, it's a privileged pod. You're not allowed to create a privileged pod, and then it will deny the request. But admission controllers need to be configured. There are some default ones that can just be enabled, but by default they are not in the plain Kubernetes. So this is a common issue. There are some other missing hardening measures that we often see. Network security, let me briefly talk about that. So by default, with a default network CNI plugin, or with most of the default ones, every pod can communicate to each other pod over the virtual overlay network. So that will be the default, but Kubernetes has network policies. Network policies are also Kubernetes objects that configure which pod is allowed to talk to which other pod. By default, all is allowed. Once you configure an ingress policy for a pod or for a namespace, then everything will be blocked except what you have specified in this ingress. And the same applies for egress. So when there is no ingress or no egress policy, then it's allowed by default. But once you define a policy, then only what's in the policy is allowed. Firewalling, so especially in large organizations that want to use shared clusters for many teams, firewalling can become a bit tricky. Within the cluster, we can use the Kubernetes network policies to manage the traffic, but network policies only know the workloads within the same cluster. So I can say, okay, this pod is allowed to talk to this other pod within the same cluster. But when it's inter-cluster, so when we want to allow denied traffic between different clusters or with the outside world, so with other legacy systems that are not running the cluster, then it's very tricky because by default the Kubernetes, the whole cluster from the outside only has one IP address. Yeah, the virtual network, the pods within the virtual network, they have many IP addresses, but to reach the pods and the services and the cluster from the outside world, there's only one IP address for all of them. So when you have a shared cluster with 10 teams, they will all have the same IP address, and that makes it tricky to filter network traffic more granularly. I can only allow the whole cluster or deny the whole cluster. I can do something on ports, on the ports, so I can do some firewalling with ports, but still it's not easy. There are some ways but it also depends on your flavor of Kubernetes. For example, OpenShift, the OpenShift Kubernetes version has some. You can configure that you have separate IP addresses for different projects and different services. But yeah, with a plain Kubernetes, it's not easy to solve. Yeah, other issues we see is some debugging artifacts left on the cluster from development, secrets in images. Even Microsoft, we found a vulnerability in the Microsoft default images last year. So when you downloaded a Microsoft image, it contained the DP API key, a static key, and this DP API key is used to encrypt certain, encrypt things with this library. And so everyone, the whole world that used Microsoft images had the same key configured, so which rendered this encryption useless. So these are some issues that we stumble upon. Multi-tenancy, it's now fixed, by the way. So Microsoft fixed it a few months after we told them. Multi-tenancy is difficult, as I said. So there are many container bypasses. So there are many ways that teams could escape their namespace. How do others do that? Like, how do cloud providers do that? So with a normal like Google GKE or Amazon AKS or EKS in Azure, basically you get your own virtual machines, and on these virtual machines your cluster will be run. There's also a container as a service offering in most of the big cloud providers, so that's kind of a multi-tenant cluster. So how do they do that to make it secure? And the answer is they don't use a plain Kubernetes, but they normally use very specific runtimes that are made for security. So the normal Docker runtime, it's not really built for security. Security is, this isolation is good and it works kind of, but it wasn't built with security in mind, so it's not considered a strong security boundary. For example, Amazon with a Firecracker, they use Firecracker in their container as a service thing, which is basically they use virtualization with KVM under the hood, and they have kind of very small and lightweight kernels. So it feels like containers, but it's actually virtualizations, and you have your own kernel and you're isolated as in a virtual machine. With Nabla containers, it's a different approach. You get a library operating system. So I don't know, Linux nowadays probably has, 300, 400, 500 system calls. Yeah? And Nabla containers only uses 7 system calls, and everything else is implemented in user space. So for example, when you want to create, a TCP socket or something like that, then that's not done by the kernel, but it's all done in user space, and you only call a write or a read to the network. Yeah? And with that approach, when something happens that would normally result in a kernel exploit, this time it would be in user space. So it would be an exploit that only affects the process. And gvisor, that's Google's approach. Yeah, you can also, in the Google Cloud, you can just enable it with a few clicks. Then you get kind of isolated, secure containers in your cluster. gvisor is similar to Nabla. They have a few more system calls. I think they use, 30, 40 system calls. But they also have, they inspect system calls and inspect the parameters and things like that. So these are runtimes that were built with security in mind. And for example, like in Google, you can just enable gvisor with a few clicks. So if you have a cluster that you want to harden and make more secure, and where you have some doubts that, or where you have multi-tenancy or other things like that, if you just want to harden it, then you can enable gvisor in these clusters. But of course, it's not only about runtimes. Yeah. So of course, these cloud providers, they have also considered many other things like networking. Yeah. So you also need to isolate different clients within your cluster, yeah, on the network. You have to make sure that you're up to date, that you have a secure configuration, secure role-based access control, and all these things. So there is much more to it than just using a secure runtime. But yeah, the secure runtime is one important component to it. Not always bad. So with containers, we get a lot of isolation between application components. So if you have a microservice architecture, before it was one application. If something happens, the whole application was compromised. Now we have many different services, and if something bad happens, the impact is restricted to the container, yeah? And then there would need to be a container escape, and it would be a bit more difficult and more tricky to really affect the whole application. So yeah, this is the good sides of it. Also, since you have smaller containers, you can define stricter security profiles. It's easier because if you have a monolithic, large application, you need to basically enable everything and give the application root to work and things like that. But with containers, I can really specify which system call should be allowed. With seccomp profiles, for example, I could harden it further with AppArmor and things like that. So I can really more granularly isolate my processes because I understand them better. I know that they only need certain system calls, that they only perform certain tasks on the network, so I can really restrict it quite granularly. Also, there are a lot of free tools, open source tools that help you identify issues in your cluster. Some of them even help you try to exploit it. And yeah, these are kind of vulnerability scanners for Kubernetes clusters. They find some of them detect image vulnerabilities, some of them detect cluster configuration issues. So there are a bunch of them that are quite useful if you want to assess your cluster. What could you do? You should harden your images, not run them as root. Remove the shell, remove the package manager, remove curl, wget. These are all tools that could help an attacker after the attacker is on the container. Cluster can be hardened. Enable seccomp profiles, for example, or consider user namespaces. Yeah, use Kubernetes network policies to also have firewalling between your services. So these are one of the most important hardening measures you could probably take. Good. Actually, yeah, I'm at the end of my presentations. If you have any questions, feel free. Thank you.
So in your experience with the cloud providers, how more hardened or less hardened compared to the default vanilla Kubernetes configuration are they?
Sorry, what compared to Kubernetes?
Compared to a vanilla Kubernetes setup, like with kubeadmin and everything, are the cloud provider provided services more or less hardened?
Mm-hmm. So actually, by default, you basically get similar security as in a plain Kubernetes. If you, for example, use GKE or EKS and things like that, you have your own virtual machines. This is how it's kind of protects you from other clusters and from other users, from other tenants. But from for example, user namespace is also not enabled. I think seccomp is probably the same. The runtime, good runtime, you probably have prior. You could use gvisor, for example. I mean, that's cool. You can enable it just with a click in the cloud, which would be more difficult to kind of deploy on your own. But probably many of the issues and most of the issues that I have discussed are quite similar in the cloud. You also only get one cluster IP address, which makes firewalling more difficult. Role-based access control is similar. You can bypass role-based access control with privileged pods. It's quite similar here. So it's not that they take care of that and you don't have to worry about. So you get your more or less vanilla Kubernetes, yeah, at least in terms of security, and you would need to do most of the things I've talked about manually yourself.
Yes, hi. Thank you for your presentation. So you said that seccomp is disabled by default, basically in Kubernetes. That's what you said, right?
Yes.
What's the reason for it? And what happens when you enable it? For example, are there more panes operating, like Kubernetes and everything?
Actually, yeah.
Thanks.
Yeah, the Kubernetes, so Docker runtimes, for Docker runtime, for example, enables seccomp by default, and some other runtimes have a default seccomp profile as well. I'm also not sure why they disable it by default. I think that there are problems with certain volumes. So volumes are kind of persistence for your cluster and for your containers, and probably they have some issues there. And since they haven't enabled it at the beginning, they might break something if they just enable it by default in a new version. So I think they are a bit worried about having, breaking something by enabling by default. But at least you have one configuration that you can now use to enable it by default on your cluster. Yeah? I don't know the reason why. I think it's just compatibility with some volume configurations and things like that.
Just one question following that. So do you have any experience with someone actually enabling it and then, breaking stuff or having problems? So what's your experience there? I mean,
when you want to enable it, I think it's quite safe to enable it with the runtime default, because that's what also Docker uses, and usually most things work with that configuration. When I, of course, configure it manually, then the chances are quite high that you break something. You have to really maybe enable it only in logging mode, then find out the system calls, and then enforce it. But of course, that's always comes with some danger. But I think it's quite safe for most environments to enable it in the runtime default mode. It's just one or two configurations in Kubernetes, and then you get what you would normally get in the plain Docker as well. Yeah.
Excellent, thanks.
Okay, if there is no more questions, thank you for your attention and see you in 15 minutes.
Thank you.